Hi everyone, this is Mrs. J, and today we're going to talk about integration by substitution, or U-sub. Alright, so I've got a little warm-up for you to try, so please pause the video and hit play when you're ready to check. Alright, go ahead and check your answers below. So remember, this is just a little chain rule review, and you'll see why in today's lesson we are going out of our way to review this chain rule. So today we're going to learn about a new integration technique called U-sub, or integration by substitution. We substitute with the letter U, so that's why we call it U-sub. So essentially, it helps us find an antiderivative of a function where the chain rule was used to find the derivative. So you can use U-sub at a very specific time. So you use U-sub when you have a product and one of the factors in the integrand, which remember is the inside of your integral. So one of the factors is the derivative of the other factor. So if you look at this first integral here, you'll see that this factor has a derivative of 4. Oh, and you see 4 right here. So this factor is the derivative of this. And if you look at this next factor, you say, oh, look, this factor, 2x, is the derivative of x squared plus 1. So it's not the derivative of the entire thing, but it is the derivative of a part of the factor. So that those are times where you can use this U-sub process. So here are the steps written out of how to use U-sub. So first you're going to identify which factor is being multiplied by its derivative. So whichever factor is being multiplied by its derivative, we set that factor equal to U. So that first step is really important. Sometimes it's really obvious what to set U equal to, and sometimes it's not. From there, once you've defined what U is, you're going to actually take the derivative of U with respect to x. So we're going to take du dx, and then we're actually going to solve for du. So we're going to multiply by dx and verify that we have that expression somewhere in our integrand. Then we're going to rewrite our integrand in terms of u and du, and then we find the antiderivative of that, which will be much easier, and it will be in terms of u. And then after we're done with that, we're going to replace u into our expression, so then our answer is again in terms of x. So really that first step of identifying what is u can sometimes be the trickiest part, and sometimes we have to do a little bit of extra work to make it to make U-sub happen. All right, so we're going to start out by finding indefinite integrals. So you see that there's no limits of integration for us here. So sometimes with U-sub problems, you could probably find this antiderivative without using U-sub, but let's do it just to practice. We'll start with some nice easy ones. So I'm going to look at the different parts of my integrand, and I'm going to try to determine which part is being multiplied by its derivative. So you'll see here that we actually have x squared, and we see that the derivative of x squared is 2x. So this is what we're going to want to set equal to u. So we're going to say let u equal x squared. So then we're going to take the derivative of u with respect to x. So du dx equals 2x, and then it'd be dx dx, which just cancels out. And then we're actually going to solve for du. So I'm going to multiply both sides by dx, so 2x dx. And we're going to make sure that this entire expression shows up in our integrand, and we can see that it does. If we're going to substitute, we would replace this 2x dx. All of this gets replaced with du. So now I'm going to rewrite my integral with respect to u. So remember, x squared is equal to u, so this becomes e to the power of u, and then I'm replacing 2x dx with du. So it just becomes e to the power of u du. And now I'm going to find this antiderivative, which is just e to the power of u plus c. So remember, when we're doing an indefinite integral, we do need that constant of integration. And then the last thing we're going to do is substitute u back out. So I'm going to replace u with x squared. So our answer is e to the x squared plus c. So again, this might have been one where you say, hey, I could do this without using U-substitution. But again, we're starting with a nice, easy one. All right, let's try another one together. So here I'm going to look at the different parts to try to identify which factor has a derivative within the integral. So I can see here, if I have x squared plus x, I know the derivative of that is 2x plus 1, which I can see right here. So I'm going to say, okay, I think the best thing to define as u is that x squared plus x. But sometimes you set something equal to u, and then you go through the process and you'll see that it doesn't actually work, so then you try something else. So if we're defining that as u, then we know that du dx equals 2x plus 1. So du equals 2x plus 1 dx. So now we're going to substitute. So I'm going to substitute 2x plus 1 dx, all of this with du. And I'm going to substitute all of this with u. So then we have the integral of u cubed du. So remember, we didn't substitute this whole thing, just the inside of this function. So it's still being cubed. Now this integral is much easier for us to find. It's going to be 1/4 u to the 4th plus c. And then we can substitute back in for u. So we could write it as x squared plus x to the 4th all over 4 plus c. And we are all done. All right, let's try another one together. So here we have the integral of secant squared of square root of x over 2 times square root of x dx. So for this one, it might make it a little more apparent what to set as u if we rewrite this as the secant squared of square root of x times 1 over 2 root x dx. So here we can look at the different parts and say, let me try setting maybe this equal to u and see what happens. So let u equal the square root of x. So du dx will be 1 over 2 root x, which we can see right here is another factor, so that's good. And then we'll solve for du, so we can make our substitution. Dx. So all of this is going to be replaced with du, and then that inner part of our secant squared is going to be replaced with u. So now we have secant squared of u, and then du. And then this integral is much easier for us to find. All right, so we know that the antiderivative of secant squared is tangent. So we have the tangent of u, and then plus c, and then last we're going to substitute u back out. So the tangent of the square root of x plus c. And we are done. All right, let's look at this next example together. So looking at the different functions, let's say, okay, I know that the derivative of tangent is secant squared, so maybe I'll start by setting u equal to the tangent of 3x. I can't just set it equal to the tangent of x because that doesn't exist in our integrand, but I can set it equal to the tangent of 3x. Now, if you take the derivative of that with respect to x, you do need to do the chain rule here. So it actually becomes 3 secant squared of 3x. So that means du is 3 secant squared of 3x dx. Now, if you look in your function, you can see that we have close to that, but not quite. But we can make it work. So we do have to do kind of a little trick here. We do see the secant squared and we see the dx. So we see secant squared and we see the dx. But what we don't see is a 3. So what we can do is imagine we actually divide this back to the other side. And we call it 1/3 du equals secant squared of 3x dx. So we can actually substitute this, which we see in our function, with 1/3 du. So that allows us to make the substitution. And it's okay to substitute 1/3 du because this is just a constant, and we know we can just move the constant out front and continue on with our integral. So I'm going to do my substitution now. Again, we've defined this as u, and we're going to make this substitution as well. So here, remember we're doing 1/3 du, so we're going to actually substitute 1/3, and then all of this is replaced with u, and then we also have the du. So to do this integral, I'm going to move the constant out front, and then this is a pretty straightforward integral, so 1/3 times, and then we have 1/2 u squared, and then plus c. So that gives us 1/6 u squared plus c, and then the last thing we need to do is just substitute back in for u right here. So it becomes tangent squared of 3x over 6 plus c. So you can see in cases like this, when you solve for du, if you have that extra constant, that's okay. You can divide it to the other side and substitute it in to replace the rest of your integrand. Now this is actually kind of a cool problem because we can actually evaluate this same integral but with a different substitution. So let's say instead of letting u equals tangent of 3x, what if I just let u equal the secant of 3x? And again, I'm not doing secant squared, I'm just doing the secant of 3x, because if I do du dx, we know that it's secant tangent. So it'd be secant of 3x, tangent of 3x, and then we do apply the chain rule, so there would be that 3 out front. So if you multiply both sides by dx, we get 3 secant of 3x, tangent of 3x, and then dx. So this is actually kind of cool because if we substitute u with 1 power of secant of 3x, we actually have the second power down here, and then we also have the tangent taken care of. Now here we still have that issue with that extra 3, but it's no big deal. We can just divide it to the other side, and then we can make our substitution. So remember, 1 power of secant is being substituted with u, and then the other power of secant is being substituted as part of this substitution right here. So again, when I do that substitution, I end up with 1/3 u du. So remember, when we substitute this, we need to include the 1/3 and the du. And then I'll pull the 1/3 out front. We get 1/3 times 1/2 u squared plus c. And then when I go to substitute u, in this case, we get secant squared of 3x over 6 plus c. So our answers are actually different, but both answers are perfectly correct. So this is kind of a cool example where you could do different u subs and you will get different answers that are both correct. All right, let's look at this next example together. So when you look at the different parts, I see a square root function, a sine function, and I see 1 plus x to the 3/2. So we probably won't want to pick the sine function, but there is some relationship between x to the 3/2 and the square root of x, which is x to the 1/2. So we could say, maybe we'll set this portion equal to u. So let u equal 1 plus x to the 3/2. So if you do du dx, the derivative of 1 is 0, and then we get 3/2 x to the power of 1/2. So we can see that we're on the right track because we have x to the power of 1/2, which we see here. But we have that extra coefficient of 3/2, which we don't see in our expression. But remember, just like the last example, we can deal with that in just a second. And I'll say square root of x, and then we have the dx. And again, to help us make our substitution, we see square root of x and we see dx. We need to get rid of this, so I'm going to multiply it to the other side. So 2/3 du equals square root of x dx. So I can replace the square root of x dx with 2/3 du. and I can replace the u, or the 1 plus x to 3 halves, with u. So that leaves us with 2/3 times the sine of u du. And then remember, we can move that constant out front to help us evaluate our integral. And now we can say, so 2/3 times negative cosine of u, and then plus c. And then we can substitute our u value back in. So we have negative 2/3 times the cosine of 1 plus x to the 3 halves plus c. And there you go. So you'll see, like, a pretty common thing with u sub is that when you're doing your substitution, sometimes the initial derivative is not a perfect match, but we can kind of move stuff around to make it work and to achieve our substitution. All right, so let's look at this next example. So here we just have the integral of cotangent of x dx. So here you're probably wondering, how do we do u sub if there's only a single function? So there's no function whose derivative is also in the integrand. So sometimes you have to do a little work before you can use u sub. So we ask ourselves, is there some way I can rewrite cotangent of x? And you can by saying cosine of x over sine of x dx. And then we can look at that, and if it helps, you can even kind of split it up like this, times the cosine of x dx. So we have two different functions here, and really we could set either of them as u. If we let u equal cosine of x, we know the derivative of cosine is negative sine. It's not the end of the world, but there's no negative within our integrand. So just to make it a little bit easier, let's let u equal the sine of x, because the derivative of sine is just cosine. So then we have du equals the cosine of x dx. So we can do our substitution. So we have 1 over u, and remember all of this right here, we're going to substitute with du. So we have 1 over u du, and then we can evaluate this integral. And we know that if your end result is 1 over u, that comes from the natural log of u. And the reason why I added the absolute values is, again, here we don't know if u is positive or negative, so you can't take the natural log of a negative number. So we put these on here to ensure that whatever this value is, it's positive. And then we're just going to substitute our u value back in. So the natural log of the absolute value of sine of x plus c. So just remember, if you ever look at a problem, you say, this isn't like one of my really straightforward integration rules, but it also doesn't look like a u sub problem because there's no product. Ask yourself if there's a way that you can rewrite the original problem before you try u sub. All right, so now we're going to look at a couple kind of cool examples of some u sub problems where you have to even get a little more creative. So if you look at this problem, whether we set u as 2x plus 1, or if we set it maybe as just the inside of the radicand, so the x plus 4, when you do the derivative of it, it's not going to equal the other part. So we're going to have to be a little more creative with how we do our substitution. So let's say we set u equal to just the x plus 4. So let u equal x plus 4. So we know that du dx is just 1, so we just essentially have dx. So we're able to substitute this out, and then we could write this portion in terms of u, so it'll be square root of u, but then we have the issue up here. This needs to be written in terms of u, but we can actually do that by defining x in terms of u from this initial part. So if u equals x plus 4, we could also say x equals u minus 4. So we can make this substitution for this x. This will be substituted with just u, and then we could replace the dx with du from our derivative here. So that will allow us to rewrite everything in terms of just u. So we have 2 times u minus 4 plus 1 over the square root of u du. And then from here we could see what we're working with. So let's distribute and combine like terms in our numerator. So we have 2u minus 7 over the square root of u du. And then for this one, this is going to be a lot easier if we separate this into two different terms. So here, if you have u over u to the 1/2, it just becomes 2u to the 1/2. And then here, this becomes minus 7u to the negative 1/2. So if we split it up like this, it's a lot easier to find our antiderivative. So for the first part, we'd have u to the 3/2. And if we want our result here to be 2, we know that we're going to be multiplying it by 3/2. So we could multiply this by 4/3. The 3's will cancel out, and then the 4 divided by 2 gives us 2. And then for the next part, this will end up being u to the positive 1/2. So if we want it to be negative 7 as the result, we should put negative 14 out front. And then we have our plus c. And then from here, we're just going to substitute back out for u. Zoom back out. So we have 4/3 times x plus 4 to the power of 3/2 minus 14 times x plus 4 to the power of 1/2 plus c. So there you go. So again, if you if you're trying your u sub and you can't really find a nice way to substitute out the other x, see if there's a way that you can define x in terms of u to help you make that substitution. All right, let's look at this next example. So for this one, we have x squared and we have square root of 2 plus x. So here we're going to want to either pick this or this to set equal to u. So let's just say, maybe don't write this down, but just watch. Let's say we let u equal x squared, so then we did du dx equals 2x, so du equals 2x dx. So if you went to try to do this substitution, we do see, okay, we could rewrite it like this, but we aren't really able to make this substitution because here the x is inside the square root, so we can't just substitute for part of that. So this this path wouldn't really work. So you could always try, say, hey, what if I set this equal to u and see if it works out? And if it doesn't, try the other part. So let's say we want let u equal to 2 plus x, so du dx would just equal 1 again. So du equals dx. So far we're able to replace this with u, and we're able to replace this with du. So we have both of those substitutions, but what we don't have is something to replace our x squared. So again, we can define x in terms of u from this initial equation. So we could say that x equals u minus 2, and then that I can use to rewrite this x in terms of u. So here we have the integral of u minus 2 squared times the square root of u, and then du. Now, to help us evaluate this integral, it's actually going to be easier for us to kind of expand this out and try to distribute in the square root of u, because right now it's a product of 2 and it makes it a little bit trickier. So let's first expand out our binomial. So we have u squared minus 4u plus 4, and then, sorry, this last 4, there you go, and then times u to the 1/2 du. And then from here, we can actually distribute this in to our trinomial, and then it's much easier to find the antiderivative. So when I do here to here, remember we're adding the exponents. 4/2 plus 1/2 is 5/2 minus 4u to the power of 3/2 plus 4u to the 1/2 du. Okay, so for this first term, it will be u to the 7/2, and we want the coefficient to be 1, so the coefficient here should be the reciprocal, 2/7. For our next term, the power will be u to the 5/2, and if we want the coefficient to end up being -4, well, this should be -8/5. So the 5 in the denominator cancels this out, and negative 8 divided by 2 is negative 4. And then for our last one, we'll have u to the 3 halves here. For this one, we want the 3 to disappear. So we'll say plus, and we'll say over 3. And we want something divided by 2 to equal 4. So it will be 8/3 here. And then we'll have our plus c. And then all we have to do from here is substitute for u. And we're done. So 2 plus x to the power of 7 halves minus 8/5 times 2 plus x to the power of 5 halves plus 8/3 times 2 plus x to the power of 3 halves plus c. So you can see by looking at our answer, this would be nearly impossible to come up with on our own without using some new technique to help us find this indefinite integral. So U-substitution is going to be a super, super valuable tool for us. Okay, so now we're going to try doing a U-sub problem with a definite integral. So the process is going to be almost the same, except once we've done our substitution for u, we need to make sure to also rewrite our upper and lower bounds in terms of u to help us evaluate. And then we'll use that FTC part 2 to help us finish evaluating. So here we can see, okay, let's try setting the radicand equal to u. So u equals 3x plus 4, so du dx equals 3. So we have 3 dx. I see dx in our integrand. I don't see the 3, but again, that's okay if it's just a constant. We can move it to the other side, and then we can replace dx with all of this. And then we're able to replace this with u, so we're ready to do our substitution. All right, so remember I'm replacing dx with 1/3 du, so I'll put the 1/3 out front, and then we have the square root of u and then du. Notice that I left these blank for right now because they used to be 0 and 4, but those are the x values. So we actually now need to adjust those for u. It's easy to do. We're just going to replace it here. So if x equals 4, then u equals 3 times 4 plus 4, so u equals 16. So that's going to be our new upper bound. And if x equals 0, then u equals 3 times 0 plus 4. So u equals 4. So now it's going to be from 4 to 16. So again, we use this to help us adjust our upper and lower bounds once we rewrite everything in terms of u. So to help us evaluate this, I'm going to move our constant out front. And now I'm ready to evaluate. So we have 1/3 times, and this is going to be, let me do this, 2/3 u to the 3 halves, and this is going to be evaluated from 4 to 16. Remember, when we have a definite integral like this, we don't need that c value. It would cancel out when we do FTC part 2. And to make this a little bit easier for us to evaluate, let's actually pull this constant out front. It will join the 1/3, and then we only need to evaluate this part. So then that leaves us with 2/9 times, we have 16 to the power of 3 halves minus 4 to the power of 3 halves. Let me zoom out a little bit. Which gives us 2/9 times 64 minus 8. So 2/9 times 56. So that gives us 112/9. So again, when we're doing U-sub with a definite integral, same process, except we need to remember to redefine our upper and lower bounds in terms of U. All right, let's try another one together. So here we have another definite integral, so now we need to look for our U-sub values. So we know that the derivative of tangent is secant squared, so it's definitely going to be the easiest route to set tangent equal to u. So we know du dx is secant squared of x, so du equals secant squared of x dx. So now we have everything we need for a substitution. We have u right here, we have the secant squared dx replacing with du. And then the last thing we will have to do, so we have u du. We're going to need to redefine our upper and lower bounds in terms of u. So let's start when x equals 0. So our lower bound, if x equals 0, u equals the tangent of 0, so u equals 0. And when x equals pi over 4, we have u equals the tangent of pi over 4, which is 1. So we're evaluating it from 0 to 1. And then we could do our antiderivative. So we have 1/2 u squared evaluated from 0 to 1. So that gives us 1/2 minus 0, which is just 1/2. So this one actually looks like a pretty, it could look like it's a kind of complicated problem, but really once we do our substitution, it's pretty straightforward. All right, let's look at this next example. Here we have the integral from pi over 6 to pi over 2 of sine squared of theta, cosine theta, d theta. So here, if we have sine and cosine, again, we could use either one as u, but remember the derivative of sine is just cosine. So let's actually let u equal the sine of theta. Notice I'm not doing sine squared. When we substitute it in, we can just call it u squared. So we know that du d theta equals cosine of theta, so du equals cosine of theta d theta. So we have everything for our substitution except for adjusting our upper and lower bounds, which we'll do in just a second. So again, this becomes u squared du. So remember, we just define u as just sine of theta. And now we need to find our upper and lower bounds. So when x equals pi over 6, u equals the sine of pi over 6, which is 1/2. And then we have an upper bound when x is pi over 2. So u equals the sine of pi over 2, which is 1. Okay, and now we're ready to find our antiderivative, which would just be 1/3 u cubed, and then that's evaluated from 1/2 to 1. So that gives us 1/3 times 1 cubed minus, here we have 1/3 times 1/2 cubed, which is 1/8. So we have 1/3 minus 1/24. So we have 8/24 minus 1/24 is 7/24. And there you have it. All right, before I let you guys go, I want to talk about one extra little tip that might make your job a little easier. So if you notice that you have some type of symmetric function, so either an even or an odd function, and again, here's those definitions of an even and an odd function, it can actually save you a little bit of time. So if you're evaluating an even function, which remember, even functions are symmetrical over the y-axis, and if you're evaluating it from negative a to a, so like -5 to +5 or -12 to +12, you could actually just evaluate half of that, so from 0 to a, and then double it, because we know that because it's even, it's just going to be reflected, and therefore that area will be doubled. Now, if you are evaluating an odd function from negative a to a, remember odd functions are symmetrical 180 degrees about the origin. So they look something like this. So we know that whatever is happening on the right, the opposite of that is going to be happening on the left. So if you're evaluating from negative a to a, those areas are always going to cancel out. So it's just going to be 0. So this especially is one that can really save you time, because you know that your answer is 0. You don't even need to find half of it. You'll just automatically know that they will cancel out. Again, this is not something that is required to evaluate these integrals, but it just might save you some time if you notice that you are working with a symmetric function. All right, so that is all for today's video. Thank you so much for watching.